So we are going to be doing ahead of the curve, which to start off with, just kind of reminding us how we solve some of these equations. When there's no b, it's easiest to factor, and so or to take the square root of both sides. And so when we're solving this one, we're going to move the 100 over, and you get x squared is equal to 36. So now we're going to take the square root of both sides, and we end up with the square root of x squared, which is, I'm sorry, my pen stopped working, which is x, and the square root of 36, which is plus or minus 6. 3x plus 5 equals 15. On this one, you're going to want to move the 15 to join the 5, because we want everything on the same side because we have that b term. And then from here, you can choose. Do you want to use the box and try to factor? Or do you want to use quadratic formula? I know a lot of y'all default to quadratic formula. Factoring with the box is often a lot quicker. I'll show you how to do that on this one. And so when I'm factoring with the box, I put the x squared in this corner, the negative 10 here. So I am looking for something that has a product of negative 10x squared that has a sum of 3x. Well, two things that multiply to give me negative 10 is 5 and 2. And if I make the 2 negative, that'll give me the sum of the 3. And so positive 5x, negative 2x, an x can come out of both, and a 5 can come out of both. An x can come out of both, and a negative 2 can come out of both. And so that means the factors are x plus 5 times x minus 2 is equal to 0. And when I solve that, I put each of those factors equal to 0. And so x is equal to negative 5, or x is equal to positive 2. And so my answers, just kind of practicing that same habit of putting these in order from least to greatest. And with what we're covering today, that's going to come into play of why that's a useful tool to have. So going on to the next one. So we have 4x squared plus 12x is equal to 7. 4x squared plus 12x minus 7. I'm going to move that 7 over to the other side. And so just to practice, we're going to do the quadratic formula on this one. A is equal to 4, B is equal to 12, and C is equal to negative 7. And so B squared minus 4AC, 144 minus 4 times a negative 7. And so from when we multiply that together, we get 28 times 4, which is 112. And that's going to be plus. So 144 plus 112 is going to be 156. Excuse me, 256. And so we have x is equal to negative b plus or minus the square root of my discriminant, all divided by 2a. So negative b is negative 12 plus or minus the square root of 256, all divided by 2 times my a, which is 4. Well, the square root of 256 is 16, so negative 12 plus or minus 16 divided by 8, which means I'm going to find the positive of it divided by 8, which is going to give me 4 divided by 8, which is 1/2. And then I'm going to do the negative. Negative 12 minus 16 divided by 8, which is negative 30 divided by 8. I can divide a 2 out of both of those. Excuse me, negative 28 divided by 8. And I can divide a 4 out of both of those, which gives me negative 7 divided by 2. And so when I write these in order from least to greatest, that negative 7/2, comma, 1/2 is my answer. Let's do one more, just kind of reminding us how we solve. And so we have x squared plus 4x minus 3 is equal to 5. I need to move the 5 over to join the other side because I want everything on the same side. And so we have x squared plus 4x minus 8 is equal to 0. A would equal 1 in this case, B equals 4, and C equals negative 8. And so we're first going to the discriminant, b squared minus 4ac. So 4 squared minus 4 times 1 times a negative 8. And so we have 16 plus 32, which gives us 48. And so I'm going to my next step, which is x equals negative b plus or minus the square root of 48 divided by 2 times a. And so x equals negative b, so negative 4 plus or minus, well, the square root of 48. Which of those perfect squares lives inside? So that 1, 4, 9, 16, 25, 36. Well, I know a 4 lives inside there, so square root of 4 times the square root of 12. Well, a 4 lives inside that square root of 12. And so 2 times the square root of 3. So 4 square roots of 3 divided by 2 times 1. And so x is equal to negative 4 divided by 2 plus or minus 4 square roots of 3 divided by 2. So negative 2 plus or minus 2 square roots of 3. And now a lot of what we're going to be doing today, you're going to actually have to take this out to the approximate answer. And so you would type this in the calculator with the 2 options. So let's talk about the projectile motion one again. We use a lot of projectile motion. It's the most common model that quadratic visualizes. And so we're going to look at the height compared to the time. So we have a firework that's shot straight up in the air at a velocity of 500 feet per second from the ground at being 5 foot off the ground. The graph is going to be represented by this function. Well, so when we're using our projectile motion graph equation, it is y equals negative 16 t squared plus VO stands for my initial velocity, so 500 times t plus my initial height, which was that 5. And so we're going to take this equation and we're going to model it by plugging it into your graphing calculator. And so if we're plugging it into our graphing calculator, we need to change our t's to be x's. And And so I plugged it into my graphing calculator, and I have a problem. I can't see it. So let's think about what each of these variables represent. The x represents our time. So when you throw something up in the air, well, let's take this as a firework. Shot up in the air. If we were to wait for what's shot up to come back down, if you've ever done the parachute one, it doesn't take long for the parachute to open up and land. So we're talking about like under a minute often, depending on what your trajectory is and how far up you're going. So if we keep using zoom out on our calculator, we're going to end up with a lot of time showing on our graph to get our height up there. So instead of that, you need to adjust your graph to only adjust what we need. I always do leave a little bit over my negatives. And so let's do a -5 as your x-min. And then let's start off with a +15. And now let's talk about our scale, our y. So our y is our height. So we're shooting it up and we're taking off and we keep going. And so we're talking about in the thousands of feet. So let's go ahead and again, I like to give a little bit of room underneath. So I'm going to do a -100. And let's see what happens at 3,000 feet and see if that covers what I need to see. So I'm going to close out my display. And when I look at this, I see it's gone up. I only put 300. That's the reason it didn't show all of it. There we go. There's 3,000. Which it's still not going to show all of it. So you can see I'm not quite to the top. I'm getting there. But if I look here, I'm not going to be able to land before that 15. So let's adjust that out further. Make a good educated guess, and I'm going to say 30. Well, when I look here, 30, it still hasn't landed. So let's make that a little bit bigger and make it at 35. Now I've landed. But we still haven't covered all my y's. So let's try 4,000. And now 4,000 has worked. So I kept adjusting my x and my y maxes until I got a graph that shows everything. Because if you do zoom out, what's going to end up happening is that a little over 30-second window is going to be way off your graph. So now we can see the whole projection of it. So the vertex is when it's going to be at its highest point. And so it's going to be roughly 15.62 when it gets to the highest point. Now that first question is asking us, when is it at 0 feet? So based upon my graph, I know it's there twice. I know it's there here. And you notice that my time at that spot is negative. Can I have a negative time on a projectile? No, because I can't have a negative time period. And then I land, and if I remember right, this is rounded. I don't think it was at 0.26. I think it rounded to 0.26. But for my purposes here, I'm going to go ahead and write down. That's going to be the only answer I'm going to give is 3.26. So my answer here is 31.26. Now, you can use, since we don't have access to Desmos when we're doing it on our test, what you can do to find that is use your trace. And your trace will be able to bring you to that point without having the Desmos where you can just click on it. And so that's going to be under your graph, and you're going to be doing it in your menus for graph. So the next one asks me what is happening at 1,000 feet. Well, only way I can find that easily is I can sit there and try to do trace and see if it would show up. But the easiest way is to create it to where you have two lines graphed. One is y equals 1,000, and the other one's the one that we have. And so y equals 1,000. Oops, I forgot to put y equals. Is going to graph here with that blue. And so there's 2 points my graph is at 1,000. Here and here. So 2.136 and 29.114. So both of those second times. And so at 2,500 feet, again, I'm narrowing that window down. And so I've got it a little bit closer, so those times are going to be a little bit closer. So 6.233 and 25.17. And so those are the two that I would record. Oh, 6.233. And the other time was that 25.7017. Those are the 2 seconds. Now that 3,900 feet is getting really close to that vertex, so they're going to be really close together in time. And so as you can see here, it's almost at the vertex, but I'm not quite there. 14.786. And then the other point was 16.464. So this is the time it would take before it's at each of those heights. And it's going to be there twice because you have it when you're going up and when you're going down. So we're going to draw a horizontal line that represents that 200. And so that line, or at that 2,000 point, that line is going to go right here. And so it asks us, when is the fireworker higher than 2,000 feet? Circle this portion on the graph. So if it's higher, it is in this section. It's above that line, but it says higher than, so it won't be touching the line. It can't touch the line. And then it wants us to draw a box around when it's below 2,000 feet. And so all this time here, well, we have up to this point and up to this point, but we're not actually there. And so those 2 points were this, oops, I forgot we didn't graph 2,000. Let me get that one done real quick. Y equals 2,000. 4.696. And the other point is 26,554. And so we want to write an inequality that represents these times. So that would be when x is less than, so it says when the firework is below 2,000 feet. So it's not less than or equal to, it's just less than 4.696. Or when I was greater than, so x is greater than 26.554. But we have another way of writing this. This is called integral notation. And integral notations say, I want to see what is the smallest it can be at. And so the smallest it can be at is going to, in this case, be negative infinity. Because if I'm going down less than this 4.696, then I'm going to be at negative infinity. And I am go all the way up till I hit 4.696. And then I am going to and so I'm going to use a parenthesis here because I have no bar underneath, so it's not equal to. And then it's going to start here, so I'm looking at greater, so that means the number needs to be listed first, and then the infinity sign. And so just so you can see how each of these things will work, I'll show you that. So I thought I had a page here for it. So if I wanted to do something like y is less than or equal to 4, that means I'm going to start at negative infinity and go all the way up till I hit 4. Because it's less than or equal to, I'm going to put a square bracket here at the 4. So it's going to go with where the number is. So like if I had y is less than 7, start at negative infinity and go all the way up until I hit 7. But it's going to be a parenthesis because there's no bar underneath it. So our smallest number always goes here. And the largest number goes here. So let's do it reversed. Let's talk about what happens whenever we have y is greater than or equal to, let's take the same number, 4. So that means my smallest number is now 4, and I'm going all the way up to positive infinity. Infinities are always going to have a parenthesis. Or, and if I said I was greater than 15, that means I start at 15, but because I'm just greater, it's a parenthesis all the way up to positive infinity. So when you have single things like this, it's just like that. But you remember those compound inequalities we had earlier this year? Something like negative 15 is less than or equal to x, which is less than or equal to 7. So my smallest number is negative 15. I put a square bracket because this bar was there. And I want a comma, and they go to my largest number. And because that square bracket's there, it's going to be or because that line's there, it's going to be a square. So let's say I had negative 12 is less than x, which is less than or equal to negative 1. So negative 12 is my smallest. There is no bar there, so there's just a parenthesis, comma, negative 1 There is a bar here because I have that less than or equal to, and so I have a square bracket. We're going to be practicing with this as we go throughout the problems today. So let's look at this next problem. First off, and I know it hasn't worked out, they showed you with working with a factoring. And again, for me, whenever we do factoring, we always use that box and the X. And so when we look here at this, let's say you wanted to do quadratic formula. So let's go ahead and do quadratic formula. And so my A was 1, my B is -4, my C is 3. So B squared minus 4AC. And so B squared is going to be -4 squared minus 4 times 1 times 3. So 16 minus, in this case, 12 gives you a 4. So we're going to plug it into the quadratic formula. X is equal to -b, so positive 4, plus or minus the square root of 4 from here, all over 2 times 1, which is 2. So 4 plus or minus 2 divided by 2. So 4 plus 2 divided by 2 is going to give me 6 divided by 2, which is 3. 4 minus 2 divided by 2 gives you 2 divided by 2, which is 1. And so my two locations X could equal is 3 and -1, or 3 and 1. So we have those two locations, 3 and 1. And we are going to go ahead and plot those on a number line. So 1 is our smallest number. And we're going to keep in mind what we have up here. So this is going to be an open circle. And then at 3, we're also going to have an open circle. And so let's go back into play. And we're going to figure out that first bit, because we had not really worked on the fact that it was less than or equal to 0 yet. And so we need to figure out all the times that if we were to be on this graph, these are our changing points at 1 and 3. And so am I going to be positive or negative in each of these spots? And as long as you choose a number that is smaller than 1, or a number that's between 1 and 3, or a number that's bigger than 3, everything's going to be the same until you hit another changing point. So let's try a number smaller than 1. Easiest number smaller than 1 is 0. So 0 squared minus 4 times 0 plus 3. That's all going to cancel out and give you 3. 3 is less than 0. Is that true or false? Well, it's false, so it can't be here. Now let's try a number between 1 and 3. So let's try 2. 2 squared minus 4 times 2 plus 3 is at less than 0. So that's 4 minus 8 plus 3 is at less than 0. 4 minus 8 is -4. -4 plus 3 is -1. So that is less than 0. So this section checks out. Now let's check our last section. Choose a number bigger than 3. So I'm going to choose 4. 4 squared minus 4 times 4 plus 3 is at less than 0. So 16 minus 16 plus 3. 3 is less than 0 is false. So this one's not working. So the only section that works is from there to there. And so this is where we go back into the play of these. And so we have a sandwich. So we're going to have something kind of like this. Except for both of them are going to match. And so you have your lowest number, and in that case, this case it's 1, to your largest number, which is 3. And we're going to put it in set notation. Now the book also likes to put it to where it says x such that is between 1 and 3. I'm not going to require you write the x such that's on any of your assignments. Just realize that's what that is, what that means. So how would it change if it was now less than or equal to? So what would be different if over here, instead of having it just less than, it was less than or equal to? Well, it would fill in these two spots, and it would change the answer to where it could include those. So this would become the answer. So it could include the 1 and 3. So 1 and 3 would be included. Was greater than or equal to. So if I was to look at it as greater than or equal to, that means it would be changing. It would be these two spots. And so that means that our equation would be from negative infinity until I hit that 1, and it said greater than or equal to, so that means it's going to be a square bracket, or it'd be from 3 to positive infinity. And these always have to have the or in the middle if we ever have it to where when you shade it, the sections that worked are in these two ends. So it would be everything smaller than 1 and everything greater than 3 if it said greater than or equal to. So if we graphed this on the coordinate plane, which is that same one that we were working with, we know our two x-intercepts are 1 and 3, and our vertex was in between it. And our y-intercept, oops, I went the wrong way, was at 3. So our graph looks something like this. How the graph supports the solution. Well, that's everything that's shaded below. And that's how it supports the solution. So Jeffrey correctly determined the roots of his quadratic equation should be 5 and 2. So we got to this step okay. But he made a mistake going forward. So see if you can find his mistake. His mistake, and I'll show you over here on the side. So he's found out that at 5 and 2 are the two locations that it worked for. And this is the reason I always do it where I show it on a number line like this. And so he chose a number. So he chose x equals 1 for this area. He chose x equals 3 for this section, and x equals 6 for this section. It doesn't matter what number you choose. It's smaller than 2, or between 2 and 5, or between 5 and positive infinity. You just had to choose a number. And so he chose a number, and he plugged it in. So 2 times 1 squared minus 14 times 1 plus 27 was wanting to know if it was greater than or equal to 7, in which he did the right and found out that 15 is greater than or equal to 7. So he said this section worked. And ours was an equal to up here, so this is going to be a filled-in circle here. Now I check the next section, and he correctly found the number. And found out that 3 is greater than or equal to 7, and that was false. So this section doesn't work. And then he gets to his last section, and so that stopped at 5. And he found out that 15 is the number that all reduces down to is greater than or equal to 7, and that works. So he correctly found the right numbers here. But what he did wrong was use the wrong numbers for this spot. He was using these numbers, which are incorrect. And what he should have used was that 2 and that 5. And so his answer should have been negative infinity until he got to 2, and we're going to close bracket, or from 5 to positive infinity. So when we're modeling the quadratic, this is just taking it from the story. So the balloon was launched from a machine upward of the height of 10 feet with initial velocity of 46 feet per second. So we're going to identify the variables. The variables are our time and our height, which is our y. And so that's at negative 16 x squared plus our initial velocity, which was 46 x plus 10. And it says to use technology to help us sketch the graph. And so this one, we're not going to go up as high. It's not talking about a rocket. So we're not going to be going up near the height that we were in the last one. And so we're not going to need quite that window. But it's going to start the same way. Negative 16 x to the second plus 46 x plus, what was the initial velocity, or initial height? 10. And you see this balloon is not going to have all this height that we were having originally. So we need to really zoom this back in. Nor is it going to be going near as long. As it looks at it, we're going to be going under 5 seconds. So I'm just going to bring this back down to 5. And then I'm going to bring this way down. If you look, it's going to be under that 500. And it looks like it's going to be under the 100. So let's try 100. And I don't need to go as far down on my negatives, so I'm just going to bring that down to negative 20. And so that gives me a better window to look at things. And so here's my graph. So my initial height was 10, so that tells me my y-intercept. And it looks like I landed at 3.078 is when it took me about 3 seconds to land. And so we want to take and graph this. And we want to know when the balloon was 30 feet off the ground. And so when I'm 30 feet off the ground, we're going to draw a line in of y equals 30. So I'm 30 feet off the ground at 0.534 and at 2.41 or 2.341. Those are my 2 points. And so we want to circle the portion of the graph that is below that. And so when we graphed it, we end up finding out that our height was at 43. It's our highest point. And so I'm just going to go over here and sketch that graph. And so at 30 feet, it'd be right about here. And this is the roughly 0.5. And this is the 2.341. And so if you want to write and solve an inequality for when it's above that 30 feet, and let's use the graph to explain it. So let's look at it. We're going to take and do negative 16 x squared. It wants to know when we are above 30 feet. So that means we're not including that 30 feet. So greater than 30. And so we have negative 16x squared plus 46x minus 20 is greater than 0. And so we're going to solve it like that was an equal. And so our A is negative 16, our B is 46, and our C is negative 20. And you probably are going to want to have a calculator for this one because this is dealing with more realistic real numbers, which means they are not nice, pretty numbers to graph. And so B squared minus 4AC is 46 squared, which is 2,116, minus 4 times a negative 16 times a negative 20, which is going to end up being subtracted. And 4 times 16 times 20 is 1280. And we're going to subtract that from 2,116, which gives you 836. And so I'm going to plug that into my x equals opposite of b, so negative 46, plus or minus the square root of 836 divided by 2 times a, which is negative 16. Well, if I type in the square root of 836, it's not going to come up as a nice, pretty number. And in this case, we're wanting to approximate anyways. And so we are going to take and find the decimal of it. So we're going to take and find the square root of 836, which is 28.914 approximately. So let's go ahead and plug that in. 46 plus or minus 28.914 divided by 32. And so I'm going to end up having to find the two numbers. Negative 46 plus 28.914 divided by 32, and negative 46 minus divided by 32. And so when you find those two numbers, the negative 46 divided by 32 gives you that 0.534, which is pretty close to what we had here. And when we did the other one, oh, that was a negative 32. And so we had the other one. We had 46, negative 46 minus 28.914 divided by 32 gives you that 2.34 number. And so we're going to do the same idea to determine when it's at or below 43 feet. And let's model it on your graph. And so let's look at the graph. And in our graph, that's almost to the vertex. And so you had 1.375 and 1.5. And so and it says above 30 feet. So that means I need to be above it. So I'd be including those, but it's not going to be those exact. And so that's the inequality. If we're writing an inequality symbol, or if we wrote it in interval notation, it would be the 1.375, comma 1.5. Oops. I wrote that the wrong way. Also get the wrong line. At above 40 is going to be that we need to be less than that 1.375. So from negative infinity up until that point, or greater than 1.5. And we're at or is above 30 feet is going to be sandwiched between these two. So 0.534, comma 2.34. And since we are above, we're not including it, so we're having parentheses. So on that getting started activity, we shot that firework straight up at an initial velocity of 500 feet per second, or 5 feet above the ground. You determined it was between 2,000 feet between 5 and 27 seconds. And what do you think is going to happen if a second firework is shot from initial velocity, so the same speed, but instead of being from 5 feet above the ground, it's going to be from the ground level? So do you think it's going to have more time or less time above 2,000 feet? Predict. Well, see if your prediction is right when we actually go through and find this. So let's write an inequality represents the second speed. So negative 16 times our x squared plus your initial velocity times x plus your initial height. And so we're going to go ahead and graph that. And so I'm going to go back and zoom out my window to that 4,000 and my y-axis to 35 seconds. Actually, my y-axis to 4,000. I put on the wrong one. And my x-axis to 35. And so we're going to see when is it above that 2,000. So at 4.71 and 26.454. So between those two time frames, it is above that height. So from just about just about 5 seconds to just about 27. So it's really not, it does change it slightly when we look at the exact numbers, but it's not far off. So it'll be about the same because we're not far off 5 feet versus 0 feet. And I want y'all to do the formative on Classroom.